Research and the Graduate Center of the City University of New York. And this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, once again, we're going to answer some of the emails that I get. I get so many emails with questions that I can't possibly answer all of them, so I apologize. And instead, I'd like to answer some of the questions I get on air. Well, let's just jump into some of the science questions I get. Once again, the first question I get is, how real is the threat of asteroids from outer space? When just yesterday, NASA announced that it will launch next month the very first spacecraft to try to intercept an asteroid, keeping in mind that this asteroid could have our name on it. The asteroid is called Bennu. It is 1,600 feet across. It is big enough to knock out London and a good chunk of England. It's not just a city buster. It's what's called a nation buster, an asteroid big enough to take out a huge chunk of Germany or England. Now, of course, these asteroids come whizzing by the Earth all the time, as we now know. We now know that we live in the middle of a cosmic shooting gallery. If, for example, you could somehow illuminate every single asteroid that's out there in outer space, and then look up at the night sky, what would you see? You would be shocked, absolutely shocked. You would see millions, literally millions of dots of light, each light representing an asteroid that could do a lot of damage to the planet Earth. So there are thousands of what are called NEOs, near-Earth orbiting objects. And we humans have been blissfully unaware of these things ever since we walked the face of the Earth. Yes, this threat is not new at all. We see ancient impact craters on the planet Earth, and if you look at the moon, you see proof of this. The moon is pockmarked by the scars of millions of impacts that have taken place over the 4 billion lifespan of the moon. So this is not science fiction anymore at all. We see craters, gigantic craters, if you photograph the Earth from outer space. If, for example, you look at the planet Earth, there's the famous asteroid crater, the Beringer crater in the American Southwest. It's a favorite spot for science fiction movie companies to photograph an extraterrestrial impact on the planet Earth, but you too can see it if you're driving across the United States. Well, Bennu, this asteroid, is a real threat. If it hit the Earth, and of course we're still debating the odds of this, perhaps 1 in 2,000, but if it hit the Earth, it would hit the Earth with a force of about 1,000 Hiroshima bombs. Not 1, but 2, but 1,000 Hiroshima bombs. You know, just a few years ago over Chelyabinsk, Russia, we had a sneak preview of this. An object about the size of an apartment building sailed over Chelyabinsk and fortunately blew up in the atmosphere, raining down also meteoric debris in the neighborhood of Chelyabinsk. No one was killed, fortunately, but it shattered a lot of windows and rattled a lot of nerves. If the Chelyabinsk asteroid had actually hit the Earth, it would have hit the Earth perhaps with a force of maybe 50 Hiroshima bombs. Well, Bennu is much bigger and poses a much bigger threat. It can unleash the force of perhaps 1,000 Hiroshima bombs, or the force of 1,450 megaton equivalents of TNT. So, what is NASA doing about it? NASA announced that next month it will launch the OSIRIS-REx lander. And what will the OSIRIS-REx rocket do? First, it'll reach the asteroid, orbit around it, land on the asteroid, and then extract 2 ounces of material from that asteroid and bring it back to Earth by the year 2020. Now, can it really hit the Earth? Well, it turns out that it regularly crosses the orbit of the planet Earth. The next time will be in 2135. When's the next time after that? And after that? Well, we don't really know. Because after it makes a pass, sometimes it goes near the planet Earth, where it may actually encounter some of the air molecules that surround the planet Earth. Yes, even in the vacuum of outer space, there are air molecules from our atmosphere. So every time it goes close to the Earth, its orbit is slightly altered in ways that cannot be predicted. Now, usually we know the orbits of these things to mathematical precision. We can calculate thousands of years from now what kinds of meteors pose a danger to the planet Earth because we have Newton's laws of motion. However, Newton's laws of motion will also work for atmospheric particles, but our computers are simply not powerful enough to accurately gauge the disturbance on an asteroid as it comes whizzing by the atmosphere of the planet Earth. So, how real is the threat? Well, the threat is real, but let's put things into perspective. First of all, a city buster, like the asteroid that sailed over Chelyabinsk, an asteroid about the size of an apartment building, that hits the Earth about once every 100 or once every 200 years. Now, you don't hear too much about these impacts because these impacts usually take place in the oceans, where there's no CNN there to record it. Plus the fact that, well, just a few hundred years ago, we didn't have many great cities. We forget the fact that the human population throughout human history was very small. We didn't have megacities back then at all. And so, in other words, there were not that many targets for asteroids to hit throughout human history, even if they hit the Earth at the rate of maybe one every 100, once every 200 years, capable of taking out London, let's say. Then you have the nation busters. And Bennu qualifies for a small nation buster. If it were to hit the United Kingdom, for example, it would easily take out London and a good chunk of southern England. It would, of course, destroy England as a viable nation, hitting England with the force of 1,450 million tons of TNT, or roughly 1,000 Hiroshima bombs. And then we have the planet killer. The planet killer hits the Earth about once every 10 million years or so. The last one hit the Earth 65 million years ago, and it was a beauty. It hit the Yucatan of Mexico, carving out a crater about 200 miles across. It sent millions of tons of dirt and debris into the atmosphere, darkening out sunlight for perhaps up to a year or so. As a consequence, vegetation collapsed without sunlight, and therefore the food chain began to collapse. Without plants to eat, plant-eating dinosaurs couldn't support their massive weight. Without plant-eating dinosaurs, the meat-eating dinosaurs died, and as a consequence, up to 90% of all life forms on the planet Earth perished as a consequence. So this is a warning sign that we do have to track these things out there. Now, of course, when you go to Congress and ask for a pittance to begin the process of tracking these things, we encounter what is called the giggle factor. The politicians start to giggle, they roll their eyes to the heavens, and then they say, next. In other words, they don't take these threats seriously at all. But there are real threats from outer space, including the threat of an asteroid impact. And so, again, we expect to have a close encounter in the year 2135. It'll probably miss. But the next encounter after that, all bets are off because, as I said, every time it makes a close pass through the planet Earth, it encounters a little bit of the atmosphere of the Earth. The orbit is perturbed as a consequence, and it's very difficult to track the disturbances into the far future. And we should also point out that my organization, the American Physical Society, it backed a press conference with Congress asking for a pittance, a few tens of millions of dollars, to reinforce our power grid against a giant solar flare. It turns out that, yes, these are real threats. In 1859, we had the Carrington event. A monster solar flare erupted from the sun, hit the Earth, and basically wiped out telegraph wires, because that's all we had back then, in 1859. Given the intensity and also the records of that incident so many years ago, we physicists then recalculated what would happen if we had another Carrington event in our lifetime. And it was a whopper. We found out that property damage would be $2 trillion. That's trillion with a T, not just a B. You would have power blackouts throughout the Earth. You would also wipe out most of our communication satellites, the Internet, GPS, all that would go out. As a consequence, our astronauts would be threatened by the gigantic radiation coming from the solar flare. And on the planet Earth, think about that. You can't have credit card transactions because all the credit card machines are out. You don't have power at night, so food begins to rot in your refrigerator. There are no rescue teams for nearby cities because they too have been paralyzed by the solar flare. And so you're going to have basically a breakdown of modern civilization as it was 100, 200 years in the past. Remember how it was 100, 200 years back in the past if you see these old movies? High-speed travel back then was getting stuck in the mud with your wagon. Long-distance communication back then was yelling out the window. Yes, we may go back to that if we have yet another Carrington event. So we went to Congress and asked Congress for a pittance, a few tens of millions of dollars to reinforce our satellites, create backup systems for power systems, reinforce them to shield them, and all we got were snickers and giggles. So much for the wisdom of the United States Congress. Well, yet another question I sometimes get in email is, what about space tourism? When am I, a tourist, going to be able to take my first trip into outer space and play with weightlessness and all the things I see on television with the space shuttle and the International Space Station? Well, all the publicity around space tourism actually grew out of a prize. We forget the fact that when you go back to the 1930s, it was Charles Lindbergh's famous voyage from New York to Paris that galvanized public opinion and set into motion what we call aviation, consumer aviation, and consumer air travel. But why did Charles Lindbergh do that? Because there was a prize, a monetary prize offered of $25,000. That doesn't sound like much to gamble your life away, but hey, back in the 30s, that was a ton of money, and Charles Lindbergh became a household figure as a consequence. Now we have something called the X Prize. The X Prize, in the spirit of Charles Darwin, gives away millions of dollars for enterprising individuals that can create certain milestones in the history of science and technology. The last X Prize was won by Spaceship One. That is a commercial rocket built with commercial funds that took tourists twice in 2 weeks to the very edge of the atmosphere. They went up 17 miles straight up. So Spaceship One, well, that rocket got the X Prize. But there are other X Prizes. One X Prize entry got permission just yesterday from the FAA to send a robotic package to the moon. It turns out that the Google Lunar X Prize package is as follows. You have to create a small communications robot, send it on to the moon, perhaps renting a commercial carrier. It has to be able to walk on the moon and then send video images to prove that it is walking on the terrain of the moon. And if you do all those things, you get $20 million. Wouldn't that be great? So if you want to win $20 million, you too can Google X Prize and find out how you can apply to win $20 million. Now, these prizes, by the way, have a history that has accelerated technology and innovation. Look at the United States Pentagon. The United States Pentagon has a branch called DARPA, and DARPA regularly creates advanced technologies. That's what it's designed to do. That's its mandate. It designed the Internet. It turns out the Internet was not created by Al Gore. The Internet was created by the Pentagon, by DARPA. In fact, in those days, it was called ARPANET, later called ARPANET, and then called the Internet. And it was not developed so that we can watch movies on our computer screens. That's not why the Internet was invented. It was invented to fight World War III. It was a device used to communicate between scientists to rebuild America during and after a nuclear confrontation with the Soviet Union. That's why the Internet is so peculiar. That's why it has no telephone book. It has no guideposts. It has no sensor. It's just an empty highway. Because that's the way we scientists wanted it. We wanted an empty highway. If we're trying to rebuild Los Angeles after World War III, you don't want a bureaucratic censor somewhere on the earth to say, can't do that. That's a dirty word. No, you're doing some serious work rebuilding America during and after a thermonuclear confrontation with the Soviet Union. That's why the Internet developed so strangely. In fact, in 1989, with the collapse of the Soviet bloc, the National Science Foundation, which had all the codes and blueprints, basically gave it away for free. Here was a military weapon that changed world history in 1989 when it was simply declassified and given to you and me, changing world history in the process. Well, DARPA has gone on to create a prize of its own. It's called the DARPA Challenge. And several years ago, the DARPA Challenge was to create a driverless car. A car that could navigate in the empty terrain of the Mojave Desert, perform a certain tasks, and come back to where it started from. That is the beginning of the driverless car. So you see that sometimes prizes like this help to jumpstart technology. Inventors in their garage sometimes get so inspired, and of course they want the cash, that they make breakthroughs in technology that were unforeseen before them. That's why the X Prize was created by an acquaintance of mine, Peter Diamandis. So the X Prize today is being offered for a lunar package to be dropped to the moon, and also a tricorder, a $10 million prize for those of you who can invent a tricorder. Now, what's a tricorder? Well, fans of Star Trek know what a tricorder is, for God's sake. It's a device a little bit bigger than a cell phone, and it allows you to instantly scan a human body for its entire medical profile. No longer do you have to put a thermometer in your mouth. No longer do you have to do a blood test. No. The tricorder simply scans your body and tells you exactly what diseases you are suffering from, exactly what your state of health is. Well, of course, a true tricorder is not possible yet. However, perhaps you can look at the rules for the tricorder and invent a version that has most, but not all, the capabilities of the tricorder on Star Trek. And then another question I get in email is, well, what about the aliens from outer space? How come they don't contact us? This is the Fermi paradox, and just last week, a group has a new theory as to how to solve the Fermi paradox. The Fermi paradox is very simple. It asks the question, where are they? I mean, after all, if the universe has so many planets out there, there must be intelligent life somewhere in the universe besides on the planet Earth. Therefore, they must be able to make contact with us. So if they're really out there, then how come we don't meet them? How come they have made no attempt to contact us, or how come we have had no luck trying to contact them? So that's the Fermi paradox. Where are they? Well, of course, everyone has a theory about this. You can go down the street, talk to a perfect stranger, and they'll have a theory about this. Kids, of course, have theories about this every time they see a science fiction movie. Well, the first response that some scientists have is, bah, humbug. That's a stupid question because they don't exist at all. UFOs, Area 51, Roswell, ha! All of that is just nothing but the imagination of a Hollywood scriptwriter. Well, however, just within the last 5 years, we've got an ocean of data about the probability of life in outer space. We have a census, for the first time in history, we have a census of the Milky Way galaxy. According to the Kepler satellite, which is orbiting in outer space, tracking these extrasolar planets, according to Kepler satellite, there are over 2,000 of these planets that the satellite has recorded, of which up to almost 100% of the stars in the Milky Way galaxy have planets going around them. Think about this. Almost every single star you see at night has a planet, usually the size of Jupiter, going around it. Well, how many Earth-like planets are there? Well, one number coming in from Kepler is about 20%. So for the first time in history, we have a census of our backyard, the Milky Way galaxy, that perhaps 20% or so of the stars in our backyard, the Milky Way galaxy, have Earth-like planets going around them. So we can now answer the question, how many planets are there in outer space? Well, the Hubble Space Telescope can see roughly 100 billion galaxies. Each galaxy in turn, we now realize, has roughly 1 billion Earth-like planets. So let's answer the question. How many Earth-like planets are there in outer space? 100 billion billion. That's a number you can write down on a sheet of paper. It is huge. It's perhaps the biggest number you'll ever encounter in a discussion. And then, of course, we don't know what fraction of them have water in the form of liquid oceans and life. However, most scientists bet that perhaps a good fraction of these Earth-like planets have oceans. If you have oceans of liquid water, then perhaps you have microbial life, carbon-based chemistry that grows on a distant planet. And then, if they're out there, how come they don't meet us? Well, A, perhaps they don't exist. B, perhaps we're simply too insignificant. Perhaps they treat us like zoo animals. They simply look at us, laugh, and move on because we're like bugs to them. Another possibility, C, is, well, they really do look at us. They really do study us, but we're simply too primitive to make contact with. I mean, if you're in a forest, do you talk to the squirrels? Do you talk to the deer? I don't. But have you ever tried to talk to the squirrels and the deer? You're probably not going to get very far because they're simply, quote, too primitive. They don't have a language that we can mutually speak. They don't have a mathematics. They don't have a science. They don't have recorded history. So perhaps it's not worth it to talk to the squirrels and talk to the deer. Another possibility is that, well, space travel is too difficult. That, yeah, they're really out there, but the distance between stars is on an order of trillions upon trillions of miles. And that's the reason why they don't visit us, because it's simply too difficult. Well, here's a new theory that's making the rounds, and that is perhaps we're one of the first planets to evolve life on it in the galaxy. You see, most stars in the galaxy are red dwarf stars. They're very dim, so dim that we didn't even realize that so many of them existed. But yeah, red dwarf planets burn very slowly, but they burn for trillions of years. Our sun has a total lifespan of maybe 10 billion years. We are halfway through its life cycle, so 5 billion years from now, the sun will pretty much eat up the Earth, and that's it for the Earth. We will wind up inside the sun. So, if our yellow star is relatively rare, it turns out that our kind of star only lasts for 10 billion years, while red dwarf stars last for trillions of years. So, in other words, perhaps our yellow dwarf star, was one of the first stars to evolve with life on it, and sooner or later, the red dwarf stars will take over and outnumber us because there's so many red dwarf stars, and perhaps that's the reason why they don't make contact with us. In other words, they're not here yet. We jumped the gun. We're one of the first planets to evolve life on it because yellow dwarf stars evolved first, but we don't last very long. We're just a flash in the pan. Red dwarf stars can last for trillions of years, ample time for life to get started. Now, of course, there are some naysayers. Some people say that it's very difficult to get life around a red dwarf star started because they're very dim. And therefore, the Earth has to be very close to the red dwarf star. And if you're too close, it's radioactive. So there are some criticisms of the theory, but yet it is another potential answer to the question, where are they? Now, my own particular point of view is this. If you're walking down a country road and you come across an anthill, do you go down to the ants and say, I bring you trinkets, I bring you beads, take me to your ant queen, take me to your leader? Or perhaps you have a strange, politically incorrect urge to step on a few of those ants. Well, if they're that advanced that they could soar across the galaxy to meet us, then almost by definition, they're going to be hundreds, thousands, maybe even millions of years more advanced than us. And at that time, we have to answer another question. What do we have to offer them? What do we, with our feeble technology, have to offer them? Because they can already span the galactic space lanes to visit the planet Earth. And so my particular point of view is that, yes, they're probably out there. The laws of probability are greatly in their favor if there are 100 billion planets out there. But we don't rate on their radar screen simply because we're not ready. We're not advanced enough for them to make contact. And so, yeah, I think they're out there. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In this part of Exploration, we're going to bring on our special guest, Dana McKenzie, who's the author of a new book that probes a question that perhaps everyone's asked themselves at some point or another, and that is, where did the moon come from? Believe it or not, there are many theories about the origin of the moon, but recently, all these theories have seemed to coalesce into a unified theory of the origin of the moon. So once again, our special guest today is Dana McKenzie, talking about where the moon came from. And now I'd like to bring on our special guest today. We're very delighted to have with us Dr. Dana McKenzie. He's a mathematician and now a science writer, and he got intrigued by the whole question of the moon. Where did the moon come from? Why do we need a moon? Where is the moon going? The ancients speculated about the origin of the moon, and now we have hard scientific data about the origin of our nearest celestial neighbor. And today we're going to be talking about his latest book. It's called The Big Splat. That's the theory that says that billions of years ago, an asteroid about the size of Mars plowed into the planet Earth, and out of the debris crystallized our moon. So once again, our special guest today is Dana McKenzie, author of the book The Big Splat, and today we are talking about the origin of the moon. How did you first get interested in the so-called Big Splat theory?
Yeah. Okay. So, well, the way I got interested in this was that I went to a conference on the Earth and the Moon, on the origin of the Earth and the Moon, in Monterey in 1998. Actually, I covered this conference for Science Magazine, which I write for pretty often. And I went to this conference and was very struck by the fact that everybody there was talking about something called the giant impact theory. The giant impact theory is what moon scientists actually call it. The Big Splat is what I call it in my book because I needed a fancier title. Now, you can't write a book called The Giant Impact. It sounds boring, but The Big Splat sounds more exciting. So, but if you actually go up to a moon scientist and talk about it, the giant impact is what they call it. Anyway, so there are about 100 moon scientists and planetary scientists at this meeting. They all talk about the giant impact theory as if everybody knows what the giant impact theory is. Now, of course you know what that is. That's just, that's the way the moon formed, and there's really not that much debate about it. And this stunned me because I had never heard of it, even though I consider myself a fairly scientifically literate person. And, as a science journalist, it's kind of my job to know about things. And I hadn't heard about this theory. And so right away that kind of raised my antennas a little bit. And I said, wow, somehow they haven't gotten the message out there about this theory. Now, here's this big question that we went to the moon to find out. Where did the moon come from? That was one of the big scientific objectives of the Apollo mission. And here they're saying we found out the answer, and yet they haven't managed to tell the public what they found out.
Okay, well, let's get right into that now. Now, everyone has a theory of the moon. We see it practically every night. Right. The ancients had theories of the moon. So talk to us a little bit about how the ancients viewed the moon, starting perhaps the Greeks and other ancient societies.
Yeah. Well, it's an interesting question because the ancients, a lot of them didn't know what to make of the moon. Some people thought it was something that was in our atmosphere. Other people thought it was a hole in the cosmos that basically is this hole that you could look through and see the heavens beyond or something like that. There were many theories. I think the two very important theories to know about are, first of all, the Aristotelian theory, which dominated the Western viewpoint for literally 1,500 years or so, which viewed the heavens as these perfect, incorruptible things that the planets and the stars all lived out there, and as I said, they're considered to be made of some different substance, something they call it the quintessence, and you had this. So, and one of the key things about this theory is that the Earth is at the center of the universe in this theory, and that all these other things are sort of ranged around the Earth. And the Earth is sort of viewed as where all the bad things are, the corruptible things that decay and die and stuff like that. And the heavens are out there and perfect. And so this, as I said, this dominated Western thought for centuries. People thought that the Earth was at the center of the universe. What's interesting is that was not the only theory, even in the era of the ancient Greeks. There were some people, there's a Greek astronomer named Aristarchus, who actually posited the idea that the sun was at the center of the universe, and actually came up with the idea very much like what we now call the Copernican system. And so actually, and in that theory, when he actually saw the sun as being the center of the universe, and the planets as being Earth-like bodies that orbited around the sun. And so in this theory, the moon was not something that was not so different from the Earth. It was just a piece of rock up there in the sky. And, of course, nowadays, that's what we know it is. So they were right. At the time of the Greeks, no one knew. There was no way to find out. What's interesting is that there was this very vigorous debate during the time of the ancient Greeks. But the prestige and power of Aristotle eventually sort of turned the debate into a very one-sided argument.
It seems fascinating to me that the Greeks actually calculated the distance between the Earth to the moon.
Yes, they did a number of remarkable things. They could calculate the radius of the Earth, and they worked out the distance from the Earth to the moon. I believe they had some idea, perhaps, of the distance to the Earth from the Earth to the Sun, although I don't know how accurate they were on that.
It's absolutely amazing to me that the Greeks could do those two calculations, the size of the Earth and the distance to the moon, and they did it using just basically string and a protractor by looking at shadows around the ancient world at noontime at a certain time of the year.
Right.
Not all shadows are the same. Therefore, the Earth must be curved, and they could actually calculate the distance, the radius of the Earth by looking at the different shadows of the planet Earth.
It's actually very mathematical. It's basic trigonometry.
And then looking at eclipses, comparing the solar eclipse to the lunar eclipse, and the fact that two are different. But both of them involve the moon. They could then calculate the distance between the Earth and the moon.
That's right. Again, it's sort of trigonometry, and we're kind of lucky, actually, that the moon is just at the right distance where during a total eclipse it just eclipses the sun. It's not too big and not too small, but just right.
Now let's talk about Galileo and the telescope. With the proliferation of the telescope, we could see craters on the moon. And how did that influence our thinking about the oceans of the moon? When we look at maps of the moon, we see mare this, mare as in mariner, as in oceans.
Yeah.
So how did the telescope affect things?
Yeah. Well, the 1600s were a very interesting time. So you had the telescope being invented about 1609, and Galileo heard about it and actually built his own telescope, which was the best telescope of its day, like 1610, 1611, or so forth. And the first thing he looked at was the moon, because that's the most obvious thing to look at in the night sky. And if your listeners haven't ever done this, you really should do it. Look at the moon through a telescope, because it just looks completely different. When you look at the moon with the naked eye, it looks kind of flat. And there's technical reasons for this. But when you look at it through a telescope, you can really see the curvature. And immediately you can just tell this is not, a flat hole in the sky, it's not, some celestial sphere orbiting up there like Aristotle said. You can tell that it's the world. And so when people look through the telescopes, they can see this. And, of course, the first assumption was it's a world like ours. And so you see these, as you said, the mares, which is the Latin word for sea. And the first theory that people had was that these were actual bodies of water. And so they named them that. And in fact, there was a big race in the 1600s to name all the features on the moon. And some people named them after, had one naming scheme, people. There's sort of a Catholic Church naming scheme, and then there's sort of a English naming scheme, and eventually they settled on naming features in Latin. So that's why we have things like Mare Tranquillitatis, which is the sea of tranquility. That's where the first moon landing was.
And these mares are actually, as I understand, lava flows, volcanoes that covered up.
Yeah. So it became evident to scientists fairly early on that they really were not seas of water. But, of course, they didn't know what they were exactly. They were just, for some reason, darker than the rest of the moon rocks. And so we didn't really know for sure what they were until we went to the moon on the Apollo mission. And the first mission was to one of these seas.
Yeah, we'll get into that in a minute. But tell us a little bit about Kepler and also the son of Charles Darwin. They also had theories about the moon.
Yeah. Well, Kepler was an interesting person to write about. One of the fun things about writing a book is that it evolves sometimes in ways you hadn't expected. I've always been a big fan of Galileo, and so I had sort of expected to write a big chapter about Galileo and how important his discoveries were for the moon and so forth. And what I found out was, well, really, Galileo didn't have that much to say about the moon. He wrote this one fabulous little pamphlet about it, and then went on to other things. He got more interested in the moons of Jupiter, and he, of course, was interested in the whole this whole solar system and so forth. So he didn't really actually say that much about the moon. But Kepler sort of was haunted by the moon his whole life, and he actually wrote the what some people consider the first work of science fiction, which is called Somnium, the Dream. And this dream is actually a dream about a voyage to the moon. And what's interesting about this, ostensibly science fiction, is that it actually has a huge amount of science fact behind it. And it's just a marvelous compendium of what was known scientifically about the moon and so forth. And, of course, Kepler was very much a proponent of the idea that the moon is another world. And he envisioned what it would be like to be on this other world. And, for example, he came up with all sorts of interesting facts. But one thing that he realized, which I'm not sure if most people realize now, is that if you're on the moon, you don't see the Earth rise and set. The Earth stays in the same spot in the sky, and that's because the Earth is tidally locked the moon is tidally locked to the Earth, so it doesn't rotate relative to the Earth. So you always see the Earth in the same point in the sky. Kepler figured this out. I don't think anyone knew that before. And so actually, when the Apollo astronauts went to the moon, the Apollo 8 astronauts orbited the moon and took this wonderful picture of Earthrise above the moon. And I think people, probably thought of that as being just like sunrise. Well, actually, the reason they saw Earthrise was because they were going around the moon, and they come around the backside of the moon and they see the Earth on the other side. But actually, the Earth doesn't rise over the moon. The Earth just stays there.
In fact, when we talk about the man in the moon, or people in Asia talk about the rabbit in the moon, it's the same devil moon. We never see the backside of the moon.
Yeah, you don't see the backside.
Yeah, because of the fact that one side is locked onto the planet Earth because of something called tidal forces.
That's right. And that is where we get to start to talk about Charles Darwin's son. And here's another one of these sort of unexpected heroes of my book. I mean, everybody knows about Charles Darwin, but very few people nowadays realize that he was actually the father of a tremendous, marvelous scientific family. That his son, George Darwin, was the greatest expert on tides in the late 1800s. And he also had his son, Francis Darwin, who was a very noted naturalist in his time. Both of these sons were made knights of the British Empire, just like Charles Darwin was. And in fact, around the turn of the century, George Darwin was one of the most famous scientists in the world. Now, people have sort of forgotten about him. But one of the things I hopefully have done in my book is kind of bring him back into the limelight a little bit. He was the first person to propose a scientifically based theory for the origin of the moon. And because he was such an expert on tides, his theory was actually based on tidal motion. But what he realized is that there are tides on the moon very much as there are on the Earth. And in fact, the Earth has a much stronger tidal effect on the moon than the moon does on the Earth. And so, in fact, the Earth has locked the moon into position. It's not able to rotate sort of independently the way the Earth does. And it creates a bulge in the moon, just the same way that the moon creates a bulge in the Earth. Now, what George Darwin realized was that the bulge, the tidal bulge in the Earth, because the Earth is not locked to the moon, the Earth is rotating, and the Earth rotates faster about its axis than the moon rotates about the Earth. So when the Earth rotates, its tidal bulge is always getting ahead of the moon, okay, because the Earth's rotation is faster. And so this bulge is actually pulling the moon forward. It's always tugging the moon forward in its orbit. And so you might think this would make the moon go faster and faster, but that's not actually what happens. When you learn a little bit of Newtonian mechanics, what actually happens when you tug a planet faster in its orbit is it moves out. Okay, so the moon is gradually moving away from the Earth. And George Darwin named this effect tidal friction. And he based this entirely on pure physics, on the pure physics of mathematics. And it's very interesting because he had no way of directly verifying this. But one of the things that the Apollo astronauts did when they went to the moon, the first mission, is put a reflector on the moon so you could shine a laser beam at this reflector and look at the way, shine it to the reflector, have it bounce back to the Earth, and actually directly measure how quickly is the moon moving away from the Earth.
Okay, let's say a few things about Newtonian physics now, okay? Newton in the 1600s came out with the definitive laws of gravity,
right,
which binds the solar system together. And he also calculated the allowed trajectories, including circles, ellipses, hyperbolas, parabolas, but there are no spirals. In free space, in empty space with no friction, spirals are not allowed as a solution of Newton's laws of motion. Therefore, capture was not possible. It's simply physically, mathematically, scientifically not possible for a single Earth in outer space to capture a solitary moon without friction, like air friction, and there's no air in outer space.
Right.
So we can actually use Newton's laws of motion to rule out one of the main theories of the origin of the moon.
Well, you would think so. But nevertheless, the capture theory was one of the three main theories going into the Apollo mission.
Right, because people didn't understand the laws of physics.
Yeah. Well, so let's actually, let me just step back for 1 second and say that the first theory was George Darwin's theory, which was called the fission theory. And so where that came from, so basically his idea of where the moon came from was that it just spun off the Earth. Okay, the Earth was spinning much more rapidly, and the moon flew off the Earth. And the way he arrived at this theory was basically by running the tidal friction scenario in reverse. So basically he saw that the moon is receding from the Earth now, and he said, okay, so I run the movie in reverse. It had to be moving towards the Earth back, if we run the movie in reverse. And so eventually when you go back to the beginning, you have the moon actually at the Earth. So that's where he got the so-called fission theory. So that was the first scientifically based theory of the moon's origin. The second one, historically to be proposed, was the capture theory. And as you say, the capture theory, a priori, if you know Newtonian physics, seems to be impossible. Okay? Now, there's a caveat you put in there, though, which is that without friction, you cannot have a spiral orbit. But if you put in some friction, then you could have a capture. And so this is very implausible, admittedly, but one of the first proponents of the capture theory suggested that maybe the interstellar medium actually has some kind of resisting stuff in it. That actually the guy who proposed this was a very colorful guy named Thomas Jefferson Jackson, an American, very self-promoting, self-aggrandizing guy, who was one of the first American astronomers to get a PhD in Europe. He was a somewhat well-respected guy in his time, but he had some really wild ideas. And one of these ideas was the idea that there was something out there in the interstellar medium that resisted motion and then enabled the moon to be captured by the Earth. very quickly that theory became less respectable scientifically. But still, there were people who argued for some version of the capture where maybe you had a lot of debris around the Earth early in the formation of the system, and that debris could slow something down enough to be captured.
Okay, well, now let's get to the Apollo space program, because you've been alluding to it.
Yeah.
What did the Apollo space program show in terms of moon rocks? What are moon rocks made of?
Right. Okay, well, so what's interesting about moon rocks is they're a lot like Earth rocks, but there are some subtle differences. So one of the things, for example, one of the ways they're a lot like Earth rocks is they looked at things like isotope ratios. And so, for example, they look at different isotopes, meaning different weights of the various elements. So, for example, you can look at oxygen, and there's a version of oxygen that's very common, and then there's some heavier versions. And these ratios in moon rocks look identical to Earth rocks. So this is a hint that the moon, wherever it formed, probably formed somewhere similar in the solar system to where the Earth is. On the other hand, there are some differences. In moon rocks, you don't see what are called volatile elements. These are elements that have low boiling points. And this posed a problem for some of the theories of the moon. Okay, the theory of the moon called co-accretion theory. The theory that the moon just sort of grew up in the same part of the solar system that the Earth did and accreted the same way as Earth did, has a problem with it because that doesn't explain why you have this lack of volatile elements. And third, another huge difference between the moon and the Earth is that the Earth has almost no core to it. In fact,
the moon has no core to it.
Yeah. It has,
I said the Earth.
Yeah. So the Earth has a huge core. The Earth has the biggest core of any planet other than Mercury.
Iron core.
The moon, yes, and this core is made of iron and nickel too, and some heavy elements, but mostly iron. Whereas the moon has a very small core. It's been estimated now at about 2% of the weight of the moon, whereas the Earth's core is about 33% of its weight. So again, if you have the Earth and moon growing up in the same part of the solar system, why does one of them get all the iron and the other gets almost none? It makes no sense. So basically, what you had is this strange situation where there are three theories for the moon, and none of them really made sense. You have this capture theory that makes very little sense because of Newtonian physics. You have to really stretch to get some way to capture the Earth. You have this co-accretion theory, which made sense before we went to the moon, but now all of a sudden we see these differences between the moon rocks and the Earth rocks. And you have George Darwin's fission theory, which also had troubles with it on physical ground. So you had three theories of the moon, and none of them seem to make sense.
Okay, now
so that's where you get a fourth theory.
Okay, now let's talk about the big splat theory. What are some of the convincing reasons for believing in the big splat?
Right. Well, so there's basically the big splat accounts for some of these things that were discovered in the Apollo program. First of all, this volatile depletion I talked about, the lack of volatile elements. Well, if you have the moon forming by a giant impact, a catastrophic impact between Earth and another planet, that will blow off a lot of stuff into orbit and some stuff out into space. And what gets blown off preferentially into space is the stuff that has low boiling point. So the big splat accounts very nicely for why you don't see volatiles in moon rocks. Second thing, the iron core. Where did the moon's iron core go? Well, the big splat actually turns out to explain this very nicely, that when you have this collision, the planet that runs into the Earth is basically destroyed. It's completely destroyed. Some of it's vaporized. A lot of it is liquefied. And the heavier elements tend to go into the Earth's core. It's the lighter stuff that tends to go into orbit. So again, the big splat explains the difference in the cores very nicely, and you can actually do computer simulations that show it work this way. And then one other piece of evidence, which was unknown before the Apollo mission, probably the biggest scientific discovery of the Apollo missions was the discovery that the moon once was covered by an ocean of magma that's molten rock, about 600 kilometers deep. And so we have evidence, and I could talk about what the evidence is if you want, but there's this direct evidence from the moon rocks that the moon surface was once molten. What provided the energy to melt the moon? Okay? Again, the giant impact theory explains this very nicely, because you have this incredibly energetic collision. You have all this stuff being blown into orbit. You have the Earth with a ring of debris around it for maybe a year, maybe 100 years, just like Saturn. But this debris coalesces very rapidly and forms the moon. And this rapid coalescence is a very violent process. You've got stuff falling into this glowing moon and basically melting the rocks. You know, the rocks hit each other, they get heated up, and eventually the outer layer melts. So again, the big splat accounts for this molten layer, this magma ocean, where none of the other theories really do. So there's no one thing that says we had this giant impact, but there's a series of things that, bit by bit add up to making this be more positive.
Well, personally, I like to say that what I find interesting about the story of the origin of the moon is that it shows you how scientists work. And that is, we start with making hypotheses about the origin of the moon, but hey, that's not enough. Then you got to look at the data. You got to look at the numbers. And now, of course, we have theories. We have the theory of Isaac Newton. We have modern chemistry. We have aeronautics, by which we can then begin to use computers to simulate these scenarios. And so, in other words, this is the scientific method in action. We propose lots of ideas. We then try to look at these ideas and see whether they correlate with data. But now we have computers. And with computers, we can do simulations of these things. And on the web, you can actually see some of these simulations where we take the moon and we take the Earth, run the videotape backwards, and then try to fill in the gaps about where the moon actually came from. And if you assume that there was an object about the size of Mars that plowed into the Earth, you can then simulate that cosmic explosion and then recreate the origin of the moon right inside the memory of a computer. Well, I'm afraid that's it for Exploration.